All right, welcome to chapter 3.4. So what you need to know about this section is that basically this whole section is just examples of how we use the idea of the derivative or the rate of change, the instantaneous rate of change. And it's just going to be example after example after example of different things that we do with this, different ways to talk about it, to use it, to apply it. So as you're going through this section, just keep that in mind that there's nothing new here. Everything we're talking about is this derivative, but we're going to just throw it on top of a whole bunch of different problems. So very quickly, let's review the vocabulary. First of all, and I've written this all out so that we could just sort of fly through it, and I'm just going to highlight it with the little laser pointer as we talk. The difference quotient. When you hear the words difference quotient, it is the average rate of change of this function over the interval from x to x plus h. So we take the change in y, f of x plus h minus f of x, and we take the change in x, which is x plus h minus x, and we make that quotient. So that's the average rate of change. And if we wanted to, we could very quickly just, sketch our little graph. You guys have seen this before. There's x plus h. And of course, this is f of x plus h. And this is f of x. So we got our change in y, we're changing x. Instantaneous rate of change is the limit as that quotient, as h gets closer and closer and closer to x. So we take the limit as h goes to 0, and we say that that's the derivative, f prime, however you want to look at it, but we're taking some specific value of x, x equals a, and taking that limit. And when we say rate of change, we imply instantaneous. So anytime you see the words rate of change, it means instantaneous. If we want the average rate of change, we will say find the average rate of change, as opposed to just find the rate of change. So let's take a look at a quick example. We know that the area of a circle is pi r squared. And if we think about why would we ever be using this problem, we'll think about tree rings, for example. We've got area, and question is this a function of radius? That area function of radius. So the rate of change of area with respect to time. Remember, that's how we say it from last chapter. Rate of change with respect to, and I said time, but of course I meant radius. And we know that the constant stays out, and we know that the derivative of r squared using the power rule is 2r. So this is just 2 times pi times the radius. The rate of change of area with respect to radius. So let's look at a couple quick examples. If the radius is 5 centimeters, then the rate of change of area will be 10 pi. If the radius is 10 centimeters, the rate of change of area with respect to radius will be 20 pi. And of course, if you go back and you look at the tree ring problem, what you discover is that we know that the rate of change of area is going to be a constant for that tree. Each year, it generates the same amount of area. So if you consider this, 1 year's worth. And so as the radius gets bigger, then those rings have to get thinner. So that's why a tree cross section looks like it does. Don't worry about the details here. I sort of getting out over my skis on this one, and we'll deal with that. We'll talk about problems like that a little more thoroughly moving forward. Okay, next video is going to be about motion on a line. Just to give you a quick preview, you've got a line and you've got some particle, and the particle can move back and forth on that line. And we'll talk about how calculus, try that again, how calculus deals with that. Thanks for watching.